On November 12, 2021, astronomer Przemysław MRZ at the Warsaw University Observatory detected something that should not have been possible to see. A planet, not orbiting a star, not bound to any solar system, drifting alone through interstellar space at a distance of 5,000 light-years from Earth, moving at 20 kilometers per second relative to the background stars, completely untethered from any gravitational anchor. The planet was not emitting light. It was not reflecting starlight. It was invisible. But for 42 minutes it passed directly in front of a more distant star, and its gravity bent the starlight around it in a phenomenon called gravitational microlensing, briefly magnifying the background star's brightness by a factor of 2 before the planet moved on and the star returned to normal. That 42-minute window was the only evidence the planet ever existed. They cataloged it as OGLE 2016 BLG 1928, a world estimated to be between Earth and Neptune in mass. Wandering the galaxy without heat, without light, without a sun. Its surface temperature, if it has a surface, would be close to absolute zero. Any atmosphere it once had may have frozen and collapsed onto the ground. And if it ever hosted life, that life is gone, extinguished when the planet was ejected from its birth star system billions of years ago. But the most disturbing realization was not that this planet exists. It was what the detection implied, because the only reason we saw it was because it happened to pass directly in front of a background star at exactly the moment astronomers were watching. The probability of such an alignment is astronomically small, which means if we detected one rogue planet by chance, there must be billions of them drifting unseen through the Milky Way, and we have no idea where they came from or where they are going. Rogue planets are not a mystery because we do not know they exist. Astronomers have suspected their existence since the 1990s, when computer simulations of planetary system formation showed that gravitational interactions between young planets could eject some of them into interstellar space, casting them out of their solar systems like stones flung from a slingshot. The mystery is how many there are, because detecting a rogue planet is almost impossible. Planets do not emit their own light. They shine only by reflecting the light of their parent star. But a rogue planet has no star. It drifts in darkness, invisible to telescopes, detectable only when it happens to pass in front of a more distant light source, and its gravity bends the light in a measurable way. This technique, gravitational microlensing, was first predicted by Albert Einstein in 1936 as a consequence of general relativity. Einstein showed that gravity warps space-time, and massive objects act as lenses, bending light rays that pass near them. If a planet passes directly between Earth and a background star, the planet's gravity focuses the starlight, temporarily brightening the star in a characteristic pattern. But the alignment has to be nearly perfect. The planet, Earth, and the background star must line up to within microseconds, an angular separation so small it is equivalent to seeing a human hair from 1,000 miles away. And the brightening lasts only as long as the planet remains in alignment. Typically hours, 2 days for stellar mass objects, or minutes for planets. Astronomer Przemysław MRZ was part of the optical gravitational lensing experiment, OGLE, a survey that monitors millions of stars in the Milky Way's galactic bulge, searching for microlensing events. Most events are caused by stars or stellar remnants passing in front of background stars. But in 2016, OLED detected a microlensing event that lasted only 42 minutes, far too short to be caused by a star. The event was designated OGLE 2016 BLG 1928. And when MRZ analyzed the data in 2021, he determined that the lensing object had a mass between 0.3 and 3 Earth masses, too small to be a brown dwarf or a stellar remnant. It was a planet. There was no evidence of a host star within several astronomical units. The planet was alone. But the most unsettling part was not the detection itself. It was the rate of detections, because OGLE has been operating for over 20 years, monitoring hundreds of millions of stars, and it has detected fewer than 10 confirmed rogue planets. If rogue planets were rare, this would make sense. But if they are common, if there are billions of them drifting through the galaxy, then the fact that we have detected so few suggests that most of them are too small to detect, too far away, or moving in directions where microlensing alignments never occur, which means the ones we have found are not representative. They are the tip of an invisible population. The first confirmed rogue planet was discovered in 2000 by astronomer Takahiro Sumi at Nagoya University. Using data from the MOA, Microlensing Observations in Astrophysics survey in New Zealand, the event, designated MOA 2007 BLG 192, is a short-duration microlensing event that lasted just a few hours, caused by an object with a mass approximately 3 times that of Jupiter. At first, astronomers assumed the object was orbiting a star, but bound in a very wide orbit that made the star undetectable during the microlensing event. But follow-up observations with the Hubble Space Telescope found no evidence of a host star. The planet was unbound, drifting freely through space. This was the first direct evidence that rogue planets exist. But the detection raised more questions than it answered. Because the planet was massive, Jupiter-sized, the kind of object that should form in the outer regions of a planetary system and remain gravitationally bound unless something ejected it. What could eject a Jupiter-mass planet from its solar system? Astrophysicist Hal Levison at the Southwest Research Institute ran simulations of planetary system formation and found that ejections are inevitable. When planets form from a protoplanetary disk, they do not settle into stable orbits immediately. They migrate, pulled inward or outward by gravitational interactions with the disk and with each other. And in systems where multiple giant planets form, close encounters are common. During a close encounter, one planet gains energy and moves to a wider orbit. The other loses energy and spirals inward. But occasionally, one planet gains so much energy that it exceeds the escape velocity of the star system entirely. It is flung into interstellar space, never to return. Levison's simulations predicted that for every planetary system like our solar system, at least one planet should be ejected during the early stages of formation. And since there are hundreds of billions of stars in the Milky Way, most of which likely formed planetary systems, there should be hundreds of billions of rogue planets drifting through the galaxy. But detecting them was nearly impossible. Until 2011, when astronomer David Bennett at NASA's Goddard Space Flight Center proposed a dedicated survey to search for rogue planets using gravitational microlensing. The survey, called the Nancy Grace Roman Space Telescope mission, would monitor hundreds of millions of stars simultaneously from space, detecting microlensing events lasting minutes to hours, the timescale characteristic of planetary mass objects. Before Roman could launch, ground-based surveys began finding more rogue planet candidates. In 2016, astronomer Nuria Mira-Roig at the University of Vienna discovered a population of young rogue planets in the Upper Scorpius Stellar Association, a region of recent star formation located 400 light-years from Earth. The planets were detected not by microlensing, but by direct imaging, because they were young, less than 10 million years old, and still glowing with the heat of their formation. Mira-Roig identified 70 rogue planets, ranging in mass from 5 to 15 Jupiter masses, all drifting freely through the association with no host stars. The sheer number was staggering. It suggested that rogue planets are not rare outliers, but a natural byproduct of star formation, ejected from their birth systems within the first few million years. But these were all massive objects, Jupiter-sized or larger. The smallest rogue planets, the Earth-sized and Neptune-sized worlds, remained undetectable. Until Ogle 2016 BLG 1928, why are the smallest planets the hardest to detect, yet likely the most common? Until now, this looked like a population count. Survey problem. A challenge of building instruments sensitive enough to detect objects that emit no light and bend starlight too faintly to see without perfect alignment. But it was not a survey problem, because in 2020, astronomer Ian MacDonald at the University of Manchester discovered something that should not have been there. A microlensing event detected by OGLE that lasted for several years, far longer than any planetary microlensing event ever observed. The object causing the lensing was not moving through the galaxy like a rogue planet. It was stationary, or nearly so, gravitationally bound to something. MacDonald analyzed the light curve and found that the lensing object was a planet, approximately 6 times the mass of Earth, orbiting a star so faint it was almost invisible. The star was a white dwarf, the collapsed remnant of a sun-like star that had exhausted its nuclear fuel billions of years ago and shrunk to the size of Earth. This was the first direct evidence of a planet surviving its star's death. When sun-like stars run out of hydrogen fuel, they expand into red giants, swelling to hundreds of times their original size. Engulfing the inner planets and incinerating anything in close orbit, the Sun, when it becomes a red giant in 5 billion years, will likely consume Mercury, Venus, possibly Earth. Any planets in the outer solar system will survive, but they will be scorched by intense radiation and stellar winds that strip away their atmospheres. McDonald's planet had survived. It orbited the white dwarf at a distance of about 2 astronomical units, just beyond the red giant's maximum expansion radius. But its atmosphere was gone, stripped away during the red giant phase. The planet was a dead core, a rocky or icy remnant, orbiting a dead star in a system where nothing would ever form again. This is the hidden barrier. The realization that rogue planets are not just ejected during formation, they are also created during stellar death. When a star becomes a red giant, it destabilizes the orbits of its remaining planets. Gravitational interactions intensify. Planets collide or get flung into eccentric orbits, and some are ejected entirely, cast into interstellar space as the star collapses into a white dwarf, which means every star that dies creates rogue planets. And since billions of stars have already died in the Milky Way's 10 billion year history, the number of rogue planets created by stellar death might rival the number created by ejection during formation. And then in 2022, astronomer Emma Softic at the University of California, Berkeley, discovered something even more disturbing. She analyzed data from the Gaia Space Telescope, which has measured the precise positions and motions of over 1 billion stars, and found that several stars in the solar neighborhood are moving in nearly identical trajectories, as if they were ejected from the same location at the same time. Softic traced the trajectories backward and found that the stars originated from a single stellar cluster that dissolved approximately 50 million years ago. When she calculated the cluster's original mass, she found a discrepancy. The stars that remained did not account for all the mass the cluster should have contained. Approximately 20% of the mass was missing. That missing mass could be brown dwarfs, objects too small to sustain hydrogen fusion and too faint to detect. But Softic proposed a different explanation. The missing mass could be rogue planets, objects ejected from the cluster during its dissolution, now drifting invisibly through the galaxy. If Softic is correct, then rogue planets are not just ejected from individual star systems. They are ejected from entire clusters during dynamical interactions, when clusters merge or dissolve, scattering their members across the galaxy. Why are planets the first objects lost when stellar systems become unstable? In 2023, NASA launched the Nancy Grace Roman Space Telescope, a mission designed explicitly to find rogue planets using gravitational microlensing. Roman's 2.4-meter mirror, identical in size to Hubble's, and its wide-field infrared camera can monitor hundreds of millions of stars simultaneously, detecting microlensing events lasting seconds, 2 days. Astronomer Matthew Penny at Louisiana State University, a member of the Roman microlensing team, calculated that the telescope should detect approximately 250 rogue planets during its 5-year primary mission, including dozens of Earth-mass objects. For the first time, astronomers would have a statistical sample large enough to determine the true population of rogue planets in the galaxy. And in March 2024, just 6 months after science operations began, Roman detected its first rogue planet candidate. The event lasted 16 minutes. It's caused by an object with a mass approximately 1.2 times that of Earth. Follow-up observations with ground-based telescopes confirmed the detection and ruled out the presence of a host star within 10 astronomical units. The planet was designated Roman 2024 P001, an Earth-mass world drifting alone through space. But the detection revealed something unexpected. The planet was moving faster than predicted. Its velocity relative to the galactic disk was 60 kilometers per second. It's far higher than the typical orbital speeds of stars in the Milky Way. This suggested the planet was not ejected from a nearby star system. It was ejected from a system in the galactic bulge, the dense central region of the galaxy, and had been traveling through space for billions of years. Astronomer Clement Rank at NASA Goddard analyzed the planet's trajectory and found that it would never return to its birth region. It was on a trajectory that would carry it through the galactic disk, out into the halo, and eventually into intergalactic space, where it would drift for eternity, isolated from all other matter. This was the proof that rogue planets are not temporary wanderers. They are permanent exiles. Once ejected, they do not return. They do not recapture into new star systems. They simply drift, cooling, darkening, until they reach thermal equilibrium with the cosmic microwave background, just 3 degrees above absolute zero. And then in August 2024, astronomers using the James Webb Space Telescope detected infrared emission from a rogue planet for the first time. The planet, located in the Orion Nebula star-forming region, was young, less than 1 million years old, and still radiating the heat of its formation. Webb's mid-infrared instrument detected the thermal glow at a wavelength of 10 microns, revealing a surface temperature of approximately 500 Kelvin. Astronomer Samuel Pearson at the European Space Agency analyzed the spectrum and found absorption features consistent with water vapor and methane, molecules that should not exist on a rogue planet's surface because they would freeze solid at interstellar temperatures. But the planet was young, it had not yet cooled, and its residual heat was keeping its atmosphere gaseous. Pearson calculated that the planet would remain warm enough to sustain a gaseous atmosphere for approximately 10 million years. After that, the atmosphere would freeze, collapsing onto the surface as ice, and the planet would become inert, invisible, indistinguishable from the billions of other frozen worlds drifting unseen through the galaxy. On November 12, 2021, Przemek MRZ detected a planet that had no sun. He did not know he was documenting one of the most common objects in the galaxy. He thought he was detecting a rare anomaly, an outlier, a world that had suffered a cosmic accident. 3 years later, we know the truth. Rogue planets are not rare. They are ubiquitous. Every planetary system likely ejects at least one planet during formation. Every star that dies likely ejects additional planets during its red giant phase. And every stellar cluster that dissolves likely scatters planets into interstellar space. Which means the Milky Way is not just a galaxy of stars, it is a galaxy of orphaned worlds, planets without suns. Worlds drifting in absolute darkness, colder than the coldest place in the solar system. Untethered from any gravitational anchor, moving at velocities that will carry them through the galaxy for billions of years. And the most unsettling realization is not that these planets exist. It is that some of them might have once been habitable. They might have formed in the habitable zones of their parent stars, developed atmospheres, accumulated oceans, even evolved life. And then, in a gravitational encounter that lasted minutes or hours, they were flung into space, their biospheres frozen, their oceans solidified, their atmospheres collapsed into ice. If life existed on these worlds, it is gone now. Extinguished not by asteroid impacts or supernova or stellar flares, but by exile, removed from the only energy source that could sustain it. And once you realize that billions of potentially habitable planets have been ejected from their star systems over the history of the galaxy, you start to understand how fragile planetary habitability is. How dependent life is not just on the right chemistry or the right distance from a star, but on gravitational stability, on avoiding ejection. How many civilizations might have arisen on worlds that are now frozen, drifting through interstellar space? Their ruins buried beneath kilometers of ice, their signals silenced by the cold. And how many more will meet the same fate in the future, ejected by close encounters with Jupiter-mass planets, or by the death throes of their host stars? Subscribe to Universe Uncovered, because the galaxy is not just stars and planets in stable orbits. It is filled with wanderers, exiles, worlds that once knew warmth and light, now drifting in eternal night, invisible, unreachable, monuments to the chaos of planetary dynamics.